knapsack. There it is. All right. So I have changed these slides a few times. 20 question decision tree. All right. So, and we haven't gone over them. And I think this is good to know because there are a few questions on the test about it. And besides, you'll need it to know it for 3101. All right. So I'm just starting here by saying, you all know the game of 20 questions, probably, right? Think of an animal, and now you can ask a question about it, right? So in this case, you think of a subset of the toys that are there a bunch of objects that some are going to go in the knapsack and some aren't, right? And you decide which ones to go in the knapsack. And then I'm going to ask you, hey, that last object, do I put it in or do I not put it in, right? And do we take the bear or not, right? So if she says yes, take it, then we put it in there, right? And then we can ask, do we take the wagon or not? And she says no, so we don't put in the wagon, right? And that follows yes, no, follows a path down this tree until you get to a leaf. And then the path is defining the entire solution, right? Every object we ask, do you put it in or not? And so the path down tells you the solution, right? And so if you were to traverse this whole tree, you're basically doing brute force. You're looking at all possible solutions, right? And that's why I didn't teach this before, is because I consider it to be a bad algorithm, right? All right, so there's the whole tree, right? And now, what is recursive backtracking? In general, I have an input, and there's a small number of things to try, right? It's like proof by, we did proof by cases the other day here. Anyway, suppose I want to prove something or solve some problem, and I don't know how to do it all at once. So one way is to break the problem into cases, right? I'm missing some kid. He's either over at school or is he at his friend's house? Cases. All right, so you do that, right? That's what we're doing. We divide into the cases. I'm trying to decide what to put in the knapsack. I can break it into cases. I either put the bear in or I don't, right? I set X to be true or set it to be false, right? You can branch here on anything you want, right? And then for each of them, we're going to solve them separately, right? We're going to loop over these things that you try. I call them answers the bird might give you, but they're just things that you're going to try, and you're going to loop over them, right? And now we're trying a particular one. And so we're going to trust that, yes, she said put the bear in. The bear is going in. We only care about solutions that have a bear in it, right? So then I say to myself, oh, I'm trying to fill a knapsack that already has a bear. Can I reduce that to a smaller problem, right? I can say, hey, put the bear in. Now I have fewer objects. Let's make it smaller. My knapsack is slightly smaller. So I ask my friend, how do I put all of these objects, the n-1 objects, into the smaller knapsack, right? It's a smaller problem. And that's where you're recursing to get help from your friends, right? So here I ask, friend, tell me how to fill the knapsack when there's no bear. And the friend does it all and gives me the answer, right? And then I backtrack. And then I say, hey, friend, I'm going to try putting the bear in. And then the friend looks at all the cases where there is a bear, right? And now what I have is I have the best answer, or all the answers, or is there an answer for this choice and for that choice, and I combine them, right? I take the best of the best. Yeah. It's a recursive program, not an iterative program. So it doesn't have a loop invariant. Well, what it does have is well-defined pre and post condition, right? If you give me a knapsack and a bunch of objects, then what's the post condition? I give you the best solution. I give you all the solutions. I give you, is there a solution, right? That's the post condition. And you need that because you need to know, what is my friend giving me and what am I giving my boss, right? Yeah. You backtrack. Well, you do all this, and then all that goes away. You delete all of that, and you start over, right? And all you do is remember just the best from over there, right? Now, people were having troubles when coding it up using the same data structure, and you put things in the data structure. Well, really, I would say delete that data structure and start over, right? Because you don't want your left and your right recursion to muddle each other, right? Right? Don't micromanage your friends or else you get confused, right? All right, so what is the knapsack problem? It's a classic, right? I have a knapsack of a given volume. I have objects. Each object has a volume and a price or a profit, right? And what you're trying to do is to say, which objects do I put in the knapsack under the constraint that the sum of the volumes I take isn't too big, and I want to maximize the profit, right? And this is just, industry wants to do these kinds of things all the time, right? It's got to make a bunch of decisions, and it wants to make those decisions that meets these constraints while optimizing the bottom line, which is how happy its customers are, right? That was a joke. All right, everybody get that? Right, the greedy algorithm doesn't work, right? Oh, so here, what we're going to do, we're going to branch, right? I'm going to look at the last object, the bear, and I'm going to ask the bird, do I put it in or do I not put it in, right? Here I'm saying, what is the last one to take? But that's not as good of a question, right? So we switch over to, do I take it or do I not take it, right? And how many answers? There's only 2 answers. So we're branching twice. And if the bird says, take it, then you put it in, and I ask my friend to fill the rest of the knapsack, right? And so what instance do I give him, right? Well, I hate this thing. Well, you can sort of see it, right? You give him n-1 objects, right? You give him everybody's, and you give him the knapsack that's smaller by the bear, right? And he fills in the rest, right? And then he gives you some solution, and then my solution is the same as his solution, except I shove the bear in the space that I let hold, right? Does that make sense? Everybody kind of follow that? I mean, it's just, yeah, right? And and then my profit is his profit plus the profit of the bear. Now, if she says don't put it in, then I ask him to fill in the rest of the knapsack the way the whole knapsack, right? I give him all but the bear, and I give him the full knapsack, and whatever he answers is my answer, right? Everybody see that? Now it's kind of, the first friend is going to give me a smaller answer because he has a smaller knapsack, right? But I add on the bear. And the second friend's going to give me a bigger right answer because he has the whole knapsack, but he doesn't get the bear. And so it's this trade-off. Right? So it's kind of like we split the set of all solutions into those that have bears and those that, right? These ones, in these solutions, I take one step up the staircase. And in these, I take 2 steps and 3 steps and 4 steps, right? And for each of those, I find the best solution, right? I recurse on each of them to find the best. And then I take the best of the best, right? Right, so what's the code, right? I'm given a knapsack with these objects, right? And for each bird answer, right, I'm going to have a subinstance, right? The first one is when she says, take the bear, I make the knapsack smaller. And when I don't take the bear, I don't make the knapsack smaller. But either way, the bear's gone, right? So I recurse on these 2. And then what's my solution? If I'm looking for the solution, then my solution is what the first friend takes. In the case we take the bear, we take his solution plus the bear, right? And if we don't take the bear, we just take his solution, right? And then we return the best of these, right? Oh, this is just saying, you know, how you store your objects so you can delete them again. I don't know, I stuck this in here. So this is just saying what we're going to do is we're going to have all the objects in an array so that we don't have to be passing them in and out. And the subinstance, we're going to just have the input is the volume of the knapsack and how many objects that you're considering in the knapsack, right? Right, so how many of those objects we care about. And the post condition is which of the first objects should you put in the knapsack so they fit, right? All right, so here's some code, right? If we have, I like the general code first. We say, well, if there's stuff in the knapsack, if we still have volume in the knapsack and there's still objects to consider, right, then we take the best of those 2. Right? Everybody buy that? Whatever best means, right? Best profit. And this one up here says, well, if the knapsack has no more space or we have no objects, then there's nothing to put in, right? Everybody good? Right, so we test what type of input we have. If a general input, my friend gets 1 less object. If we take the bear, we decrease the volume. We add the object, the bear back in, right? We turn the best of these 2 solutions. Don't micromanage your friends, right? If the knapsack's too small, you have no objects, then we don't have no objects in our solution, right? We handle all these cases, right? Everybody get that? All right, so here's a little thing where I'm being silly, but it shows you some silly things that you can do. All right. So what happens if the bear doesn't fit? Right. Then this number here, we got the mouse on the right screen. Mouse on this screen, or get the mouse here. Right. So if the bear doesn't fit, then this number becomes negative. Right. So you could very well test it right here and say, if the bear doesn't fit, don't do this example, right? You could do that. And, right? So you can stick in here code that says, if the bear is bigger than the volume, don't call the first friend, right? You could do that. And, or you can trust your friend no matter what, and then you throw in here an extra condition that says, hey, if you ask me when the volume is negative, then say no. You put too much in there. Stop. This is bad. Right? Everybody see the choice there? Everybody good with that? All right. Right. So then why did I put in this extra case? Well, you could say for software engineering, it's handling more cases. Or you could say, yeah, it's handling more cases, so my friends, I don't have to worry so much. Right? Right? And now we're saying, no, this is not a good solution. Back off. Right? We say the quality is negative infinity, right? It's really bad. Right? Why do I do this? It amuses me. All right. Everybody, let's see what, oh. Right? So then, right? It tries all 2 to the n solutions. Right? Same as brute force. Right? So dynamic programming, which we'll do next year, makes this a little faster, but still exponential time. So then we have various modifications. Everybody get that so far? Right? So let's try to do some modifications. The first modification is right? So here we're saying that we either put the bear in or we don't put the bear in, right? But maybe there are a lot of bears and you can put as many bears as you want, right? Or maybe you're walking up a staircase and you want to know you can take as big of a step as you want, right? So that's here. So how do we modify the code? Is you have a loop where you try all these options, right? Here you loop over all the possible bird answers, all the possible number of bears you put in. And if you're putting in I bears, then the knapsack gets smaller by I bears. And you add the I bears back in. Right? Everybody get that? So this says we're returning the best solution. Each, right? So here we're returning the best solution. So each one's giving a solution, and we return the best of these, right? So here I'm taking, this is a solution, and this is a solution. I want the best, right? But maybe I want to return the value of the best solution, right? And then each is providing a value. So now the friend is giving me the value of the best solution, and I'm adding on the price of the bear to get the value of the better solution, right? And then when I take the best, I'm returning the best value, not the best solution, right? And, or maybe you could return both, right? So maybe I want to return all the solutions, right? And that was in some cases, right? So each provides a set of solutions. So here we're providing a set of solutions, and I return what? Right? This is a set of solutions. This is a set of solutions. I union together. I get a bigger set, right? I think you guys know all this, right? The number of solutions, right? This tells me how many solutions have this form, how many solutions have this form. So I return the sum of those, right? I might want to turn Boolean. Is there a solution, right? I think you did that for subset sum, right? So each says yes or no. So what do I return, right? I return the or. Was there a solution this way? Was there a solution that way? Right? That's what we did. Oh, and then subset sum has this extra thing that, what's that? That's scary. Who did that? I don't know what the hell that is. But subset sum, you have to say, if it doesn't fit the base case, if it's not fitting exactly, then you say it's not a solution, right? If you have still, oh, here, this is, right? If your knapsack still has volume and you've run out of objects, right, then you don't have a solution because we want to fill the knapsack up perfectly, right? And that's all I had to say about knapsack. Did that help? Excellent. How are we doing for time now? 5 minutes. Isn't it amazing? Sorry I talked fast, but we do only have 5 minutes left. I love that answer. Yes. Yes. Once things, yeah. So you've asked this before, and 2 to the n times n to the 100, right, is bounded by 4 to the n, which equals 2 to the 2n, right? So this is all in 2 to the theta of n, right? So I guess my answer is once it's exponential, I don't care if there's an extra linear factor, right? I just, right? It's just too big. So you're right. It's probably there's an extra n factor there, but I'm not going to worry about it. Can you what? Can you solve the knapsack problem? Well, let me tell you, for the knapsack problem, it's what we call NP-complete, meaning if you had a polytime algorithm for it, then you would be as rich as Elon Musk, and so we just don't have one, right? So no, you can't solve this problem with a simple algorithm that we know of. Anybody else? Huh. I think it's important to separate out iterative algorithms versus recursive algorithms. I mean, you're not really. You're not really. What are we doing? We're doing knapsack is here. So this is kind of what the algorithm does, right? In any path down the tree, it's kind of like what you're saying. Put it in, don't put it in. right? It's considering the objects one at a time, right? But it's really, the code does it recursively. I go over here, recurse, and over here, recurse. There's not a loop where I'm looping over I, looping over the objects.
Check if either you have the element inside the set or not, or no.
So this code has no loop. You don't. No, you don't. So here I have two friends, one who puts the bear in, one who doesn't, right? So they call their friend. Yeah, because I'm given n objects, and I give my friend n minus 1 objects.
That's sad because he's getting n minus 1 object.
Yeah, so any path down this, there's me and my friend has n minus 1, his friend has n minus 2. No, there's no loop. I mean, here, if you want a center algorithm, right? If this is an array, my routine on this array of size n, I call on an array of size n minus 1, right? So I give it, and I'm given one smaller, right? And then he calls his on n minus 2 on n minus 3. Yeah, yeah, yeah. All right, so we're going to meet here on Monday with enthusiasm. We're going to put our little bubbles on the bubble sheet.
So the email I sent, right? I want it to be a bit strange for the programming test. Jackie said don't book it without the log exam center, which makes complete sense.
Right.
But for the written test, for accommodated students, he's doing on the 19th, like March 19th.
For the, yeah, so if you're talking, there's two types of, there's the programming tests, and there's the multiple choice written test. All right. So I'm doing the latter, Monday's test. How are you doing Monday's test?
Like on the 19th of January.
I don't know, Monday, whatever, a week in 4 days from now. Oh no, when is it? It's on Wednesday. No, yeah, it's Monday, right? It's this next Monday.
Yeah.
Right.
But Jackie sent an email that for the written test, all accommodated students, they do on March 19th.
Well, I would ignore him. I mean, are you sure he didn't talk about programming tests?
No,
Right? So to do the programming test, you have to book a room with computers. And he has a room for all the people who get longer time.
Here's what, like, I won't say the manual, but like the one thing that what's it called that Jackie sent out